Log on, tune in, find out. Another good idea from Cambridge.
So we'll make a start. First of all, let me remind you, if you have brought a mobile phone into the room, will you please not just switch it to silent mode, actually switch it off. Because there's this recording going on, and if any signals come in on a mobile phone, it interferes with the recording, it actually interferes with the projection. So some of you have been here for some time, and you were here in the workshops when we already had this non-stop presentation after presentation. We're not in that mode anymore, but we're in the mode where anyone can volunteer to give a seminar at any time. It's nice if you can give a bit more than a week's notice, because then we can advertise it properly and getting it coming up on the screens. So the nice idea is that people can come and give talks about work in progress, work they're doing here, and other people can interrupt them and ask questions. So just before we get into that, for those of you who've just come in, if you have a mobile phone, please make sure that it is switched off. Not just silent mode, absolutely switched off. So now I'm very pleased to introduce Hervé Monod. He's from l'Institut National de la Recherche Agronomique, based just outside Paris, and he's going to talk about work that's building on work done by André Kobylinski about the construction of flexible fractional factorial designs and how it's going to be implemented in R. So Hervé, over to you.
Thank you, Rosemary. So, in fact, a preliminary remark is I will show quite a lot of R code on the screen, and maybe the people who are in the last rows, it will be a bit small, so don't hesitate during the talk to come closer. So first, of course, I would like to thank the Isaac Newton Institute and the DAE program organizers for inviting me. It's been very useful and very interesting. So I'm here, in fact, until the end of the week, and I will come back in December. So if people want to discuss later about the talk, of course, it will be with pleasure. The second preliminary remark is to give credit of most of what I'm going to talk about to André Kobylinski, who is a researcher at INRA. Unfortunately, he's on a long disease vacancy at the moment. But what I will give some references, more precise references, but really what's behind I will show is due to his work, and my contribution is to turn it into R software. Okay. I will make a very short introduction, a bit of bibliography, but very short bibliography. And then what I want to show you is that the library we are doing allows to construct quite various regular fractional designs. So we'll start with the most standard case, which is a fraction with two-level factors. Then I will talk about asymmetric fractions. First, with only one prime number involved, so a mixture of two-level and four-level factors, and then mixtures involving different primes. And then I will talk about multi-stratum designs. So first, maybe I will go fast for some examples, but the idea is to talk about symmetric split plot design and asymmetric split plot design as examples. In fact, from 2 to 4, I will talk about the construction of what is called a design key. And this is a matrix which allows to construct the actual design, but this is not the actual design. So in the last part, probably I will have to go a bit fast, but I will say a few words about going from design key to the design. So, introduction. I said it would be a very short bibliography. So there are papers by Mike Franklin, by Desmond Patterson, by Rosemary, in the 70s on the idea of constructing fractions, regular fractions, through design keys. So I will explain later more precisely what the design key is. But it's a matrix which gives the defining relations, basically, of the fraction. André Kobylinski has worked a lot. He's been interested in the papers by Rosemary in this paper, for instance, other ones, and he's worked a lot on the subject in the 80s. I've cited a paper where I am co-author, but there are a few others. Unfortunately, some of his results have not been published, but so he developed the idea of the design key, and this led to the first version of the planar design, which I will, the planar software, which I'm going to present. Just a mention to say that it's still an active field of research. So there is, for instance, a paper in 2008 by Piston and Rogantin on mixed fractional factorial designs, and they propose a definition of a general definition of a regular fraction, which corresponds to what we construct in the planar software. So as I said, there are unpublished works, and in fact, the algorithm in the software I talk about is completely described in an unpublished paper of André in 1994, which is called Automatic Generation of Asymmetric Regular Designs. And André has programmed this algorithm in a software which is called Planar. The first version is hardly usable today, so we had the idea about 4 years ago to turn it into a R version and into a R library to make it available to more people. So here it's also a very quick review of what exists, and probably it's not complete. So I'll be interested if some of you can help me to be more precise on this point. But to construct regular fractional designs, I think to my knowledge, the main reference is the procedural factex of SAS, which is in a quality control module, and it really constructs regular fractions, but only symmetric regular fractions. So the factors must have the same number of levels, at least until recently. And I've seen, since I'm here, that there has been quite a strong improvement of this part of the SAS software. Although I think it does not construct exactly the same designs as I will present today. In GenStat, for instance, these other softwares, there are possibilities to construct regular fractions, but often, including in several R libraries, you have to know the keys, you have to know the defining relations, and then the software constructs the actual design. So here the idea is to start from the model and the terms to estimate, to deduce a key matrix, defining relationships, and then to construct the design. So actually this is done in a recent package of R, FRF2, by Ulrike Gromping from Germany. But apparently it is restricted to 2 level factors at the moment. So I think, but I may be wrong, but I think presently there is no at least easy to use tool to cope with possibly mixed numbers of factor levels, quite flexible model assumptions within the context of regular fractions, and also something which I will show with the multistratum designs, integration of hierarchy constraints between the factors. So let's start with the classical example of a design for 4 treatment factors at 2 levels, A, B, C, D. We assume there are only 8 units available, so we must do a fraction. And the model of interest is a model consisting of the main effects and the 2-factor interactions. And we just want to estimate the main effects. So this is known, this sort of requirement is known as a resolution 4, the requirements for constructing a resolution 4 design. And the solution is well known. We start with constructing a complete factorial design on the first 3 factors A, B, C. We use +1 and -1 to identify the levels of the factors. It forms a cyclic group of order 2, and so by multiplying the terms we remain in this group, and this allows to construct a 4th factor A, B, C by a component-wise product of the levels of A, B, C. So these columns are actually the columns of the X matrix of a linear model. They are mutually orthogonal. They are associated with the main effects and, for the last one, an interaction, etc. So I suppose also it is known by most of you that by constructing such a design, we introduce aliasing relationships between factorial effects, which can be summarized in this way. So 1 designates the general mean. It is confounded with the 4-factor interaction. The main effect of A is confounded with the interaction B, C, D, and so on. So finally, what we can say is, from a practical point of view, if we assume that the interactions of order 3 or 4 are 0, then the left part until there is null. So the main effects are confounded with no other effect, and they are estimable. The 2-factor interactions are confounded mutually, so they are not estimable independently, separately. Only their sum can be estimated by this fraction. So the idea which is important to keep in mind here is all the properties below can be deduced from the first line here. So what's important in a regular fraction is to know which effects are confounded with the mean. And because there is a cyclic group structure behind, all the relationships below are deduced from the first one. So for instance, the first here is obtained by multiplying this one by A. So we get A equals A squared BCD, and because we work modulo 2 here, A squared is equal to 1, so it gets erased. And it is the same for the lines below. For the rest of the talk, it would be more convenient to work with additive notations. So I present the same design with additive notations. We use integers modulo 2 instead of plus minus 1. And another difference is here I have another way of identifying the units. Instead of calling them 1, 2, 3, up to 8, I identify the units to the level, to the combination of levels of 3 factors at 2 levels. Okay? So in fact, in the design, the level A has been completely confounded, identified to the first unit factor, so the first column here. The factor B has been completely confounded with the second unit factor, C with the third unit factor, and D can be considered as the addition modulo 2 of A, B, C, and it can be also considered as the addition modulo 2 of U1, U2, U3. So this can be summarized in a matrix, which is the key matrix. I'm going. So we call it phi, in fact. So the rows are identified to the unit factors, which I call U1, U2, U3, and the columns are identified to the treatment factors, A, B, C, and D. So A, B, C are on the design are exactly the same as U1, U2, U3. So the first part here is the identity matrix. And D is defined as the sum of U1, U2, U3 modulo 2. So the last column is a column of ones. So if you have this matrix, you can construct the design. But in addition, this matrix contains information on the confounding relationships, and the important property here is that alors, I must introduce a notation. So I will denote a factorial effect by a to the power alpha, with alpha belongs to the integers modulo 2 to the power 4, because I have 4 factors. Can you read, or is it too small? So, for instance, if I take alpha equals 0, 1, 1, 0, fine. It corresponds to the factorial effect a power 0, b power 1, c power 1, d power 0, which is interaction BC, because power 0 gets eliminated. So the interaction BC is associated with the vector 0, 1, 1, 0. The general mean, of course, it's associated with the null vector. And so on. So the important property is that if alpha belongs to the kernel of the matrix phi, then alpha is confounded, a to the power alpha is confounded with 1, the mean, the general mean. So this is the first part, and the second part is that if alpha minus beta, it is a consequence, belongs to the kernel of phi, then the factorial effect a to the power alpha and a to the power beta are mutually confounded. So this matrix is a key in two ways. First, because it's the key to construct the design, and second, because it's the key to understanding the confounding aliasing relationships between the factorial effects in the design. So now I show how to construct this design in using the R library planar. So who knows R here? So about half the people. So the idea is it's an interactive software. So we get into a R session, and then the first thing to do, of course, is to load the library. Well, of course, I don't know, but it's to load the library. So it's just technical here. And then I will show two ways. We have two syntax to do that. So this is more decomposed. So first thing is to give the information on the factors. So here, so this is, we allocate to the object which is called x1.fac. It's a name I have chosen. Planar power factors is a function of the library of planar. So it's a command. And its arguments are called factors and levels. So here we specify that we have 4 factors which we want to call A, B, C, D, and they have 2 levels each. Then we give information on the model, which we are going to store into this object x1.mod. So the function here is planar point model. And here we use, in fact, the syntax of R for model formulae. So here we have the main effects, A plus B plus C plus D. And here we have all the 2-factor interactions. So here we just say that in our model there are main effects and 2-factor interactions. And the second argument we use is estimate. And here we say we just want to estimate A, B, C, and D, the main effects. By default, if we don't use estimate, it is assumed that we want to estimate all terms in the model formula. So what we have not given yet is information on the units. And in fact, we give it in the command which will make the search. So this command is called planar point design key. It will store its results in an object which is called x1.key, and its arguments are the factors. Here we have stored them in this object. The model, we have stored the information in this object. We specify that there are 8 units available, and here, in fact, we specify that we want to use the first 3 factors to make a complete factorial design. So the base argument just says that we want this first part of the matrix to be the identity matrix. It makes the search faster. So this is a shorter way to do the same thing. So we load the library. And in fact, we can specify all the information in the last of the 3 commands I have shown in the previous slide. So the factors, so here it's just for R users or to tempt you to use R. Instead of defining, well, there is an object which exists in R which is called letters. So I take the first 4 letters of the alphabet for the factor names. This is the same model, estimate. So this is also a shorthand notation for the formula. I take A plus B plus C plus D and I develop up to order 2, and the rest is the same. This is information which is printed when the planar point design key command runs. So in fact, it gives an idea of the algorithm. I will detail them if you ask questions, but I will not detail it very much in the main talk. So the first step is an analysis of the model and estimate specifications. And what's important to know is the factorial terms which must not be confounded with the general mean. Because if you remember this property, the problem is to find a matrix phi, a key matrix, such that the effects of interest or the differences between the effects of interest in the sense that is given here do not belong to the kernel of phi. Maybe I can come back here to be just a bit more precise, or even here. The idea is the following one. I want to estimate A, and there is B in the model. So A must not be confounded with B. So the difference in the sense that is given here between the factorial effect A and the factorial effect B must not belong to the kernel of phi. So A minus B, so A minus B here the main effect of A, it is A to the power 1, B to the power 0, C to the power 0, D to the power 0, and B is equal to A, B power 1, C power 0, D power 0. So the difference between, when I say the difference between A and B, I mean the difference between this vector and this vector. So 1, 1, 0, 0. So it must not belong to the kernel of phi. But in my model, there is also, for instance, the interaction BC. So A, B, C, which is the difference between A and BC, must not belong to the kernel of phi, and so on. So for those who are familiar with regular fractions, it is evident. But maybe not for everybody. So this is the first step. The second step here is not interesting. It's because we will see it later. Here it detects, then there is an analysis of the factors. All the factors are powers of 2, so the algorithm will make searches for a matrix phi involving integers modulo 2. It starts the search. It detects that there are 3 predefined columns because we have used 3 base factors. It visits the column 4, it finds a solution. By default, it stops when it finds the first solution. So now we can print the result of this search, and we get the matrix which I have written on the board. We can ask information on the aliasing relationships, and we get this unaliased treatment effects, the main effects, and the aliased treatment effects, the relationships which were written in the first example. We find the confounding relationships which we have seen before. Yes, we just a side remark. In the function alias, which is a function of the planar library, there are 2 arguments. The object which contains the key matrix and the model containing all the terms for which we want aliasing information. So this is the end of and the summary of what has been found. So this is just to go a bit further, but I will go very fast here. Of course, we can, people who know about regular fractions know that it's possible to add factors, but with stronger assumptions on the model. So if we assume there are only main effects in the model, we can go up to 7 factors. Now, the first 3 columns are the same. We use them as basic factors, but the algorithm has to find 3 columns associated to 4 columns associated to the additional factors. So it tries to find the 4th column, then the 5th, and so on. And finally, the result is the following one. One solution is to have D equal to AB, E equal to AC, F equal to BC, and G equal to ABC. Okay, and if you use these confounding relationships in the fraction, you can estimate all the main effects. Of course, the aliasing relationships are now a bit more complicated. If we look at the aliasing relationships in the model involving the main effects and the two-factor interactions, we find that the treatment effects are unaliased, so they can be estimated. No, sorry, I'm wrong. We find that the main effects are confounded with two-factor interactions, so if we assume they are 0, they can be estimated. What's this one? Yes, there is also another function to summarize the properties of the design key, and here it's another command, which is another function which is called summary, and which gives all the effects which are confounded with the general mean. So it's another way to look at the properties of the design key. Okay, do you have any question or?
Yeah. Do you generate orthogonal designs only? I assume regular orthogonal designs, your solutions?
Yes.
Do you give maximum resolution design, minimum aberration design?
Or no. In fact, I will talk about this aspect at the end, but in fact, what the algorithm does is by default, at least, it's an exhaustive search along the tree of possible solutions. So, for instance, well, if in the cases I have shown, there is only one solution, but if we suppress one factor, we have just 6 factors. There are several possible solutions, and they are not equivalent with respect to aberration. So, if you look for a minimum aberration design and you want to use this software, first, maybe it's not the best idea at the moment, but what you have to do is to let the algorithm run and find all possible solutions, and then have a function to calculate the aberration of each solution to extract the best design with respect to aberration. But it doesn't go directly to searching a minimum aberration design.
Sorry, does it take long? Because I had some experience with constructing these designs. When n goes larger, for instance, from 16 to 32, it could take pretty long. Do you?
Yes, the one item in my conclusion about the weak points of this is that it is not computer efficient. So it can be made more efficient, but at the moment it is, from my point of view, its quality is its flexibility, but not its speed. So if I do a problem a bit larger, then it can be long, and it will be longer than other software which exist.
I think my question actually complements William's, because if you're doing something like minimum aberration, you're essentially saying, for example, all words of length 3 are equally bad or equally good. Whereas I think you didn't show it in your example, but when you put in the model, you might say put in some 3-factor interactions, sorry, but not others.
Yes, exactly.
So this has the flexibility, am I right, that although you could use a nice shorthand, you could actually write out something like A plus B plus C, and then put in the 2-factor interaction AB, but no others.
Yes, exactly.
You can actually do that.
Yes. And in fact, the first examples I have shown, I think I show them because they are well known and maybe easier to understand, but they are not the examples where this software is the most efficient compared to other software, clearly. If you want to build a not too big design, it's okay, it's possible, but Comparing to some papers, recent papers on finding a minimum aberration designs which explore all possible solutions with as many factors as possible, of course it's not good.
How the choice of argument base affects the result?
Pardon?
How the choice of argument base affects the final result?
In some cases it may, not in the examples I have shown. In the examples I have shown, there are the examples are completely symmetric with respect to the factors, with respect to the numbers of levels, and with respect to the model. So in fact, it is one way to take account of these symmetries. So now I am in the second part of my talk. So we deal with asymmetric fractions. So in the first example, suppose there are 2 factors at 4 levels and 3 factors. 2 factors at 4 levels and 4 factors at 2 levels. So it's here, we take 6 factors, 4. So this is our syntax to repeat 2 4 times. This is a shorthand to say that we want a model with main effects and 2-factor interactions, and we want to estimate the main effects. We consider 32 units. So here there are 4 by 4, 16. By 2, 32, and there are 3 more factors to include in the design. So we are going to make a fraction 1 upon 8. And we use as base factors the first 2 factors at 4 levels. So this is a size 16, and 1 factor at 2 levels. So the idea is quite simple. A is a 4-level factors. So we can identify its levels with the combinations of levels of 2 factors at 2 levels. So 0, 0, 1, 1. And of course, the main effect of A includes the main effect of A1, the main effect of A2, and their interaction. And so there is this decomposition must be processed when analyzing the model and estimate part, and when constructing the design matrix, the key matrix. So here there are 2 factors at 4 levels, so 2 to the 4, and 4 factors, so 2 to the 8. So there are 8 columns to construct in the matrix. And here's the solution. Identity matrix up to C. This forms the basic factors. And then D is equal to A1, B1, C. So it's really an interaction between 3 of the real factors. E is equal to A2, B2, and C. So it's also a 3-factor interaction. And F is equal to A1, A2, B1, B2. See, it's not sufficient to say that. It is necessary to study the effects generated by these columns. But they satisfy the constraints imposed by the model and estimate constraints. So at the moment, the information that is processed remains at the level of these. So we call them the pseudo factors. It's here that the term pseudo factor is comes in. So A1, A2 are pseudo factors to represent the factor A at 4 levels, and so there is information on the confounding. So I go a bit faster. It is known that constructing a regular fraction when all factors have levels that are powers of the same prime is different from constructing regular fractions when several primes are involved. So here's an example. Suppose you want to construct a row column design, 6 rows, 6 columns, with 2 treatment factors at 2 and 3 levels. So in fact, I've called this example Latin square because it's basically what we are going to construct. It's just a way of presenting the problem. So the factors, we call them row, column, A, B. They have 6, 6, 2, 3 levels. I will not talk too much about this block argument because it's not necessary. Really, it's just useful for the output, but I'm not sure it works properly. So now the model we want to estimate is a model with additive block effects, so row effects, column effects, and main effects and interaction of A and B. There are 36 units, and we want to use the row and column factors as basic factors because they structure the units. So this doesn't change anything to the first work that Planner does, which is analyzing the model to find which factorial terms must not be confounded with the mean. It changes the second line, ineligible pseudo-factorial terms, because now, for instance, the factors at 6 levels are decomposed into one pseudo-factor at 2 levels, one pseudo-factor at 3 levels, and they correspond to different primes. So in fact, in addition to the decomposition into pseudo-factors, there is also separation of the problem, of the search, in one part which is dedicated to the powers of 2, and one part which is dedicated to the powers of 3. So I will not go into details. Note just that there is a search for prime p equal 2 and a search for prime p equals 3. And the solution in each part are very simple here. You may confound there are 6 rows. They have been decomposed into a pseudo-factor row 1 at 2 levels, 6 columns pseudo-factor col 1 at 2 levels, and A has 2 levels. And we can take A equal to the sum of row 1 and col 1. And it's okay because the interaction between rows and columns is not in the model. And similarly, here it's the same solution for the prime 3 design, but it's not the case in general, of course. And then when you ask information about the solution, at the moment the output is divided between what happens for the prime 2 part and what happens for the prime 3 part. So here there are confounding relationships for the factors at 3 levels, factors of pseudo-factors at 3 levels. And if you have questions, I'm going a bit faster, so I hope it remains clear. Of course, when we will construct the actual design, we will have to recombine the pseudo factors into the initial factors. So the third type of examples I want to show is multistratum designs. So it's an example which is well known to the people working in agronomy. So there are, in fact, I think here, 4 big blocks which we call replicates. You may assume they are row of plots in an agriculture trial. Each replicate is divided into 4 sub-blocks. So this is rep 1. This is sub-block 1 of block 1, of rep 1. And within each sub-block there are 2 plots. So you imagine it's divided into 2. And so on. So this is the block structure of the design, and we assume that there are 2 factors of interest, 2 treatment factors. The first factor has 3 levels, and the second factor has 2 levels. I take the classical case of a split plot. And in a split plot, the kind of problem you have is that it is not possible for technical reasons to vary the levels of A within the subblocks. So A must remain constant here. It can vary from here to here, but it must remain constant within the 2 plots of the subblock. So how do we specify that? So first we give the names of the factors. They have 4 blocks, 4 subblocks per block, 4 levels for A, 2 levels for B. And here is a new argument of design key. It's called INRA, like hierarchy, and it specifies. So it's a way, it's a proper syntax. It's a way to specify that A cannot vary within the combinations of levels of rep and sub. So this is one combination of levels of rep and sub. So all the 2 plots which are inside must have the same level of A. So this is the first way to specify the specificities of the split plot. And the second way is that instead of having just one model and one list of terms to estimate, we have 2 here. So the first one is what we may call the intra-block stratum. So if we put in the model the replicates and the effects of the sub-blocks, well, sorry, this is the complete model, the more complete model we want to use when we have a split plot. So replicate effect, sub-block effect, the interaction between the 2, and for the treatment effects, the main effects of A, the main effects of B, and their interaction. This is the syntax to specify that we want to cross the factors A and B. But so this is the model part, and this is the estimate part. So in the estimate part, you can see that A is absent. A is necessarily confounded with the subblocks, so we know that if we put them in the model, they can't be estimable. So this is the model estimate pair for the intra-block stratum. we want to estimate the main effect of B and the interaction, but not the main effect of A. And the second model estimate pair corresponds to what we want to do interblock. So interblock, well, the way to specify it in the planar library is that we don't put the subblock effects. So if we assume that subblock effects are 0, then we want to estimate the main effect of A. So in fact, why is it important, this second part? We know that A is confounded, so it will be constant in these pairs of plots. But still there is the rep factor in the second model estimate pair, so we want A to be orthogonal to the reps. So we want all 4 levels of A to be present in fact, the 4 subblocks that are present in each replicate. So behind the analysis of the model is a bit different, but it's exactly the same algorithm. We deduce from these specifications the factorial terms which must not be confounded with the mean. We decompose into pseudo-factorial terms when some numbers of levels are not prime. Here there is just one prime involved too, so there is a search for the solution. And the solution is here. So in fact, there is just a detail, but we have specified for the basic factors rep and sub, which are at 4 and 4 levels. We have, in fact, so this corresponds to a size 16 design, but we have 2 plots per subblock, so in fact the design is of size 32, so it has the program has created an additional unit factor which is called U star, and which corresponds to the replicates within the subblocks. And the solution is given here. What you can see is that A1 and A2, the pseudo factors associated with A, are linear combinations of the columns, here trivial linear combinations of the column of sub 1 and sub 2. So this is a condition to satisfy the hierarchy constraints which has been given at the start. And B is identified to U, and so it is completely orthogonal to the rep and sub pseudo factors. So I won't detail here the results. I won't detail the other example on the split plot design. The only difference is that now we have 4 replicates of 3 subblocks of size 2. So there are 2 primes involved, but the idea is the same. So instead of having 4 subblocks, we have 3 subblocks per block. And A has 3 levels, so we can do the same sort of idea, and it will work properly. So finally, I just want to say a few words on what to do after finding the design key. So the first thing we may want to do is compare several solutions. So in fact, this is an answer to your question. There is an option which is in the design key function, which is the maximum number of solutions after which the algorithm should stop, and this option is set to 1 by default. But it can be set, for instance, to infinity, and if you have time enough, or if the problem is not too big, you can wait for all possible solutions, and then apply some function to find to calculate a criterion such as aberration on each solution and find the best designs. you may also want, if really it's not just for fun, you may want to construct the design. And to randomize it. Construct the design, it's very, very easy. It's just matrix calculations. And randomize, it's a bit more tricky, but it's okay. So here's the syntax. So we have found a key. It is stored in an object which is called split point key. And we apply to this object a function which is called planar point design. And one argument of this function is information on how we want to randomize the design. So in the example of the split plot, we want to randomize according to this nested structure. We want to randomize the replicates. Well, in fact, it's an orthogonal design, so it's not useful, but still it works in this way. We're going to randomize the replicates, the subblocks within the replicates, and the units within the subblocks. So the algorithm is based on the generalized rest products of permutations, which Rosemary has studied, and André had also worked on an algorithm to perform these general kinds of randomization. So here is the result. I have worked it a bit because it's not evident. So replicate by replicate. So the first column here is the replicate number. The second is the subblock number, level of A. So you can check that it's confounded with subblocks. And it's different because it has been randomized. The order is different in each block. And the levels of B, which have been randomized within subblocks, so 1, 2, 2, 1, 2, 1, etc. So finally, to summarize very rapidly, so as we have already discussed, the advantage is mainly that it's quite flexible with respect to the kind of design that can be constructed within the class of regular designs. It starts from the user point of view. There is a model, and it ends in a randomized design. And of course, if the speed is not too much of a problem, if the problem is not too big, it's very easy to try several solutions, to see that one solution is impossible because one specification is impossible to satisfy because there is no solution, to try to simplify the model and run again, etc. And a nice thing is that the R environment allows to go further if you want to. The limits, of course, it's we construct regular designs, so it's only orthogonal designs and regular designs, which is a smaller class than the class of orthogonal designs. And it is, at present at least, not at all optimized with respect to computing time. So perspective, increased flexibility, increased speed, and input in the software final selection criteria, because it's true that nowadays, at least in the symmetric cases, it's really important to use refined criteria, more refined than just resolution, for instance. But at least in the case when there is, there are things to be done when the problem has symmetries. At the moment, they are not increased at all. And of course, the last word is if people want to test, I can send an address. The idea is to put it on the CRAN site soon, but it's not yet done. But there is a site where the software can be obtained. So thank you for your attention.
Thank you very much, Hervé. Are there any more questions or suggestions at this stage? So William.
Yeah, just a technical question. So, for instance, if I want a 32 by say 8 orthogonal designs, it could take a while for the computer to find all those designs. Did you save some of the intermediate results on the computer, or every time somebody wants to find a design, the program basically starts from scratch? Which is the way you are taking?
The way is starting from scratch.
From scratch.
Yes.
So it might take, for instance, like an hour. Could that be the case?
Yes.
Of course, I'm exaggerating, but
No,
for the larger case, it could take a while.
Yes, it may take an hour, or it may take centuries. For instance, the whole set of examples which I've given here, it runs because I've done the talk, I've prepared it on the Swift, so I compiled the R code each time and then the LaTeX code. This is just a few seconds, one or two or three. So for short examples, it is really very fast. But as soon as you have a bit more complicated examples, it may be slow or very slow.
Did you ever consider using the current catalogs of orthogonal designs? For instance, I know all 16-run designs are available, and 32 designs, probably most of them are available. Did you ever consider storing those designs on the computer so that next time somebody wants a design with 16 or 32 runs, it could be a lot faster?
My idea is that this software should be part of a more general software, maybe included in Planner or connected with other software, to be able to get solutions more rapidly when they exist and when they are available, certainly. But at the moment, it was just simply quite a lot of work already, and so we've just concentrated on allowing this algorithm to work properly. But then I agree with you that there is another problem, and I think this, from what I've understood reading rapidly, for instance, it's what we have done in SAS, is to mix search procedures with catalogs to find bricks to construct designs or to get the solutions directly if they exist. But at the moment, it's not the philosophy of this package.
I'm sure if this is questions but comments, there's two things that I really like about this. One is that it ends up with your randomized design. I mean, this is just from my own experience working with people. They tell you what they want, you've got to do a lot of work, you make a nice design, you randomize it, you show it to them, and at that point someone says, oh, I can't possibly do that because I can't have these ones over there, or I can't change that often. And so I think that's a crucial part of actually any general use package. You've got to be able to actually present the randomized plan to the people so that they can see whether that's usable. And the other thing I really like is it's not just fractions. You can have multi-stratum designs. But it does seem to me, you and Kobe obviously know how to do this. There's some cleverness in things like that. So just using this idea of you give the model and what you want to estimate, and you can do that more than once, and how you adapt that to a multi-stratum design would take some experience, I think. I mean, I'm very impressed by it, but that seems to me to be the key to the fact that you don't have to have a separate algorithm for every different block structure. That where the cleverness goes in is choosing the list of models. Yeah.
Yes.
So that bit impresses me.
Am I right in thinking that in that split plot you gave the structure for the construction as rep star subblocks, so that it actually would have a Latin square that it would produce for the top stratum because they're crossed, and it was only when you randomized it that it becomes randomized for subblocks within reps?
Yes. Yes, in fact, here there's a bit of. I agree that in the specifications we give for the search, we don't follow exactly the design, the structure. It should have been subblocks should have been nested within blocks, and in fact, this is just a detail, but it requires a bit of work to implement the interpretation at this stage, at the initial stage, of a formula with nesting relationships. So presently, the planner does not interpret for the model estimate specifications. You must specify. You can specify cross relationships, but not nested ones. And of course, because we know we have a bit of expertise, so we know that we can get exactly the solution we want for a split plot design. But it's true that there is a bit of trickery here.
It's just that Rosemary and I are currently working on a paper where we find that we construct designs that might have crossing, and then you actually randomise it for nesting. And there seems to be, there's a difference between the systematic arrangement that you start off with and then the design that you actually employ. And the systematic arrangement might have properties that when you randomise it go sort of thing. And there's sort of finding you need to make a distinction between the systematic arrangement that you construct and the design that you actually.
But in fact, yes, I think that something. Well, I've said there is just a detail to solve, but I'm not sure it is just a detail. So probably it requires some thought, and I agree that it's an interesting question. So at the moment, if you want to construct a split plot with planar, you have to specify subblocks and reps as a cross factors.
Well, if there are no more questions, please can we thank Hervé again for a very interesting talk.